Hey, glad you could join us. Thanks for being here. It means a lot to have you along on this quiet little journey. Wherever you are, whatever time it is, I hope you've found a soft place to settle. Maybe you've dimmed the lights. Maybe you're resting your head and letting the day melt away. That's perfect. Just you, me, and the stars above us. If you like listening to quiet stories about space and stars, please tap the like button. It helps others find this peaceful place too. And if you want to come back for more calm journeys through the universe, please like and subscribe. Enjoy what I do here. And let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. Hey everyone, today we're looking into stars, but not just any stars. Today, we're drifting far beyond the usual sparkle of night skies to meet something far more explosive, more sudden, and more mysterious: gamma ray bursts. These are the fireworks of the cosmos, not the kind that make you say ooh and ah on a summer night. These are the kind that, if we were too close, would simply erase us from existence. But don't worry, we're far away, far enough to watch safely, to hover quietly like invisible stargazers, watching a universe that sometimes whispers and sometimes shouts. Let's begin gently. Imagine a star, not just any star, but a giant, something so big that if we tried to measure it, we'd run out of numbers before we finished our coffee. You and I are floating beside it now. Feel the heat? It doesn't scorch us, not here, not in this quiet story. It just brushes your skin like the warmth of a sunbeam that snuck in through your window. This star is old, not in the tired way, but in the noble, ancient way. It's done a lot of shining in its time, fed entire planets with warmth, held its solar system like a lantern in the dark. But even giants grow weary. You might notice, just at the edge of this giant, little flickers, trembles, really, like the star is sighing. That's because deep inside, in a place no eye can see, its core is starting to change. It's running out of fuel. The fire that's kept it alive for millions, even billions of years, is beginning to dim. And that changes everything. When a star like this dies, it doesn't just go quietly into the dark. It collapses, in on itself. In a moment so fast you could blink and miss it, this whole massive thing folds, caves, and vanishes into something denser than anything you've ever imagined. And out of that collapse, a burst, a flash, a scream of energy so bright and powerful it would light up the universe like a camera flash in a cave. That's a gamma ray burst. Now let's float back a little, farther, a little more. Good, we're safely out of reach now. Watch with me, see that thin, narrow beam shooting out from the poles of what used to be a star. That's it. That's the burst. It's not just light. It's the highest energy light the universe knows how to make. Gamma rays. Not the soft orange glow of a candle. Not even the white-hot sting of a lightning bolt. No, this light cuts sharper, flies faster, and fades more mysteriously than anything else we've seen. Reach out your hand. Just for a moment. Not too close. Feel that? It's not heat you're feeling. It's the echo of power, not the kind that destroys. The kind that reminds us just how vast this place is, just how small and lucky we are to be watching from a distance. Now, don't worry if it's hard to picture how something so quick, something that lasts just a few seconds, could matter so much. Gamma ray bursts don't last long, but they speak loudly. They are the universe's exclamation points, moments where everything that was calm becomes electric. Whole galaxies blink toward them. Instruments here on Earth and far above it spin to attention. Somewhere, a scientist's coffee goes cold as data pours in from a telescope orbiting silently above our heads. Picture yourself drifting alongside me now, just past the edge of a distant galaxy. This one's shaped like a spiral, curling like a slow-motion pinwheel. There, inside one of its arms, a tiny spark goes off. You might not even notice it at first. But then the light comes, narrow, precise, and blazing. For just a few heartbeats, that one burst outshines every single star in that entire galaxy. All of them, hundreds of billions of stars, all dimmed by this one flash. And then, as quickly as it appeared, it fades. You might wonder, where do these things come from? Are they all born from dying stars? Some, yes, but not all. Some gamma ray bursts don't come from collapses at all. They come from collisions, violent hugs between dense, dead stars, neutron stars to be exact. Imagine two of those spinning, dancing, drawing closer over billions of years until they finally touch, and then, boom, another burst, another flare, another brief, blinding message in the dark. Let's move toward one of those now. Feel how the space around us warps just slightly? That's gravity playing its games. These neutron stars are heavy. So heavy that a teaspoon of their matter would outweigh a mountain. And when they collide, the burst that follows isn't just gamma rays. It's gold. Literally, elements scatter. The dust that will one day become rings, coins, jewelry. It's born here, in chaos and light. Take a breath with me. In and out. We're safe. These bursts, for all their might, are rare. They don't happen every day, not near us. The universe is big, and most of these flashes happen far away. We're just lucky, so very lucky to have eyes, lenses, and minds tuned well enough to catch them when they do. You see, every gamma ray burst is like a cosmic postcard, a quick, brilliant hello from the past, because that light we just saw, it's ancient. It started traveling long before humans built pyramids, before Earth had continents, before fish figured out how to walk. And only now, only in this quiet moment, with you and me drifting here together, did it reach our eyes. Let's imagine we're still floating, just the two of us, weightless and calm in the soft silence of space. The burst has faded now. What's left behind isn't just emptiness, it's a mark, a footprint of what once was, the remains of a star, or the aftermath of a cosmic collision. A region stirred up, glowing softly, like embers after lightning. It's easy to forget sometimes that destruction in the universe so often leads to creation. You might notice, drifting closer, that the space around us feels a little strange. It's not just empty. There's a kind of tension in the dark, a pressure you can't quite name. That's the result of energy, wild, raw energy having just been released. Radiation, still crackling faintly. Particles, still chasing each other in invisible races. And in the middle of it all, often hidden, is something even more mysterious. A black hole. Yes, quite often, after a gamma ray burst, a black hole is born. Not always, but often. Picture it now, resting quietly where the star once shone. It doesn't glow, it doesn't roar. It simply waits, a hole in the fabric of everything. No light escapes it, no sound, but its presence is undeniable. It tugs at space itself, bending time like soft wax. Now, don't be afraid. We're not getting too close, just close enough to feel the awe. The kind of awe that makes your chest tighten and your mind stretch a little wider. You're safe with me, always. We're just here to observe. Let's drift upward above the galaxy. Look down with me. See that streak of light, frozen in motion? That's the path of the gamma ray burst, still traveling outward. It could go on for billions of years. Maybe it will pass by some lonely planet one day. And on that planet, maybe someone will build a telescope and wonder what that strange flicker was. Just like we're wondering now. Isn't it beautiful? You might be wondering how we find these bursts at all. After all, space is huge. There's no warning bell, no countdown, just a sudden flash in the dark. But out there, orbiting far above Earth's atmosphere, we've placed silent watchers, space telescopes, instruments that never blink. Their only job is to scan the sky and wait for that unmistakable signal, the high-energy whisper of a gamma-ray burst. When they catch it, they alert the world. And astronomers, wherever they are, drop what they're doing and look up. Some of these bursts are so far away that the light takes over 10 billion years to reach us. That means the explosion we just saw happened before Earth even existed, before the sun was born. Let that thought settle in your mind like a pebble dropping into still water. A single event, so long ago, still shining into now. And what's even more humbling, we only see the bursts that happen to point toward us, because these explosions don't scatter light in all directions. They fire narrow beams, like a lighthouse sweeping through the void. So for every burst we see, there might be dozens, maybe hundreds more, lighting up in other directions, unseen. The universe doesn't show us everything, only glimpses. But those glimpses, they're enough to change how we see everything else. Now feel the silence again, that deep, endless hush. Gamma ray bursts are violent, yes, but the space between them, the universe between them, is vast and quiet, like a museum after hours. The bursts are moments of noise in a long symphony of stillness. You might be wondering what would happen if one of those bursts aimed right at Earth. It's a fair question. After all, they're powerful. More powerful than anything we've ever created or even imagined. If one were close enough and pointed exactly our way, the burst could strip our atmosphere in seconds. Life, as we know it, would change or vanish. But don't worry. The odds of that are so small they're almost impossible. Like winning the lottery 1,000 times in a row and then getting struck by lightning on your way to collect the prize. Space is huge. Our sun's neighborhood is quiet, peaceful. So instead of fear, let's feel something else. Gratitude. Gratitude that we get to observe these events from a safe distance. That we get to be the quiet audience to the universe's wildest moments. Let's float a little farther now, past clusters of stars, past swirling gas clouds, past planets that spin with their own secrets. Look down there, below us, is another distant galaxy. This one looks like a whirlpool, caught in time, and just on the edge of it, a tiny flicker, a soft pulse, like a match being struck. That's the start of another gamma-ray burst. You might think of it like a heartbeat. The universe doesn't tick with clocks. It pulses with energy. It breathes in these rare, extraordinary events. Look closer now. Just before the burst, there's silence. Total, thick silence. It's the hush before the storm. The star is collapsing again, folding into itself like a paper fan closing in one swift motion. The pressure builds. The light gathers. And then, it happens. The beam cuts through space like a blade. Bright, narrow, relentless. For a few seconds, it is the brightest thing in the known universe. And then it fades. As if it were only ever meant to say hello and then vanish forever. Reach out with me now. Let your fingers drift through the invisible ripple it leaves behind. That ripple might one day help form stars, or become part of a planet, or drift through a nebula until it's caught by a newborn sun. Nothing in space is wasted. Even the most violent events lead to something new. And that's the quiet secret of gamma-ray bursts. They are both ends and beginnings, death and birth, collapse and creation. One star's farewell is another star's first whisper. You and I, here in the stillness, get to witness that, not just as observers, but as part of the story. Because the atoms in our bodies, in your hands, your bones, your breath, many of them were born in ancient explosions like these. Not just gamma-ray bursts, but the supernovae that came before them. The great silent fireworks of deep time. You're made of that stardust. We all are. You might notice that after every gamma-ray burst, space doesn't look quite the same. It's not scorched, not in the way fire leaves behind blackened wood, but it's changed. The matter that was there, the star, the dust, the invisible fields has been reshaped, rewritten. What was once calm has now been stirred into something new, maybe a ring of gas expanding slowly, maybe a jet of particles racing through the void, threading space with energy like a cosmic embroidery needle. Let's move toward one of those jets now. It looks like a line of light, but it's more than light. It's a storm of particles, moving so fast they seem frozen. Like raindrops in a photo paused mid-fall. If you reach your hand toward it, you won't feel wind or pressure. You'll feel something stranger. The buzzing edge of speed itself. The hush of momentum. These particles were buried inside a star just moments ago, and now they're traveling across galaxies. Now look behind you. See that faint shimmer? That's the afterglow. Gamma-ray bursts come in two parts, the burst itself, and then the slow fading trail of X-rays, visible light, and radio waves. It's like the universe saying, wait, don't go, there's more. The afterglow can last for days, sometimes weeks. That gives astronomers time to measure, to study, to trace the burst back to its home. Some have found bursts in bright, busy galaxies, others in quiet, lonely ones, where stars live isolated lives. Every burst has a story, and every afterglow is its signature. Let's drift closer to one of those stories. This one happened over 7 billion years ago. A long-dead star collapsed and gave off a flash that lit up half the observable sky for just 2 seconds. Our satellites caught it. The data flew through space, through cables, through servers, into the hands of someone sitting in a dark room, blinking at a monitor. 2 seconds, that's all. But in that time, more energy was released than our sun will put out in 10 billion years. Let that thought sit with you for a moment. 10 billion years of sunshine, all squeezed into a moment so short you could miss it while tying your shoes. Now imagine you're there, not too close, but close enough to see the outline of the event. The darkness isn't silent. It crackles, not like firewood, but like potential. Everything in this moment is alive with consequences. The energy released will travel across the cosmos, pass through dust clouds, bounce off distant planets, maybe even be absorbed by a speck of ice floating in the darkness. That ice might melt, shift, tumble, and that tiny shift could start a cascade, a chain reaction that changes the orbit of a moon that hasn't formed yet. That's the scale we're talking about. One burst, endless consequences. Now come with me. Let's drift to the edge of time. No, really, we're heading to one of the earliest bursts ever recorded. This one came from a galaxy so far away that its light has been traveling toward us since the universe was just a few 100 million years old. That's infancy. That's the cosmic cradle. And yet, even then, stars were dying. Even then, bursts were happening. Picture it, a baby universe, still stretching, still figuring itself out, and already lighting up with the drama of stellar life and death. Look around. The space here is different. It's more crowded, more chaotic. Clouds of gas clump together like soap bubbles, forming the first galaxies. There's no Earth yet, no sun. But there is light. And here comes the burst, faint to us now. But in its moment, it was everything. The brightest thing in existence. You and I, floating through this early era, are like ghosts peeking into a nursery where stars are being born and dying all in the same breath. It's hard not to feel small out here, but small doesn't mean insignificant, because the very fact that we can see these bursts, measure them, understand them, that's extraordinary. It means our minds are big enough to hold the universe inside them, even if just for a moment. And here's something else to think about. Some gamma-ray bursts might be telling us more than we realize. There are theories, ideas still being explored, that these bursts might be tied to the birth of black holes, or even stranger objects we haven't fully imagined yet. Each one is a clue, a riddle, a postcard from a place we can't visit, signed only with a flash. Let's glide past another one now. This one's already fading, just a faint trail of light curling away into space. But if you squint there, at the very end, you can see a tiny spark. That's matter condensing, cooling, beginning to form something new, maybe a neutron star, maybe a disk of dust that, over eons, will spin itself into a solar system. Now drift with me to a quiet part of the sky. It's dark here. No bursts, no flashes, just the gentle glow of background stars. This is where we wait, where we listen. Our instruments are tuned. Our minds are open. The next gamma-ray burst could come from anywhere. It could be happening right now, billions of light years away, and we won't know until the light arrives, perhaps tomorrow, perhaps 10,000 years from now. That's the strange thing about space. The past and the future are always touching. Light doesn't care about your schedule. It travels at its own pace, delivering stories when it's ready. All we can do is be here when it arrives. You might wonder what happens to the planets nearby when a burst goes off. Well, if there are planets, and they're unlucky enough to be in the path, it's not good. Atmospheres can be stripped away, surfaces scorched. Any delicate chemistry like the kind that builds life would be erased in seconds. But again, this is rare. Most bursts happen in places far removed from where life tends to take root. It's almost as if the universe knows how to be dramatic, but also how to be kind. Still, these events shape galaxies. They sculpt star formation. They pump energy into places that were once cold and still. In their violence, they bring movement. In their death, they plant seeds. That's the beauty of the universe. Nothing is wasted. Everything becomes something else. Let's float a little farther, past the remnants, past the trails of light, toward the soft curve of a galaxy turning slowly in the dark. If you look close, you'll see stars at every stage of life. Young blue ones, hot and restless. Older yellow ones, calm and steady. And there, at the edge, the dim ember of a star that's almost gone, waiting for its final act. Maybe tomorrow it will go quiet, maybe in 1,000,000 years, but when it does, the burst will come, fast, bright, unforgiving, and somewhere, far away, someone might be watching, just like we are now. As we drift along the edge of this quiet spiral galaxy, Let your eyes follow the curve of its arms, stretching out like ribbons, speckled with stars that blink slowly in the distance. Somewhere within those arms, another massive star is nearing its end, not with a whimper, but with a silent promise. A promise that, when the moment comes, it will blaze one last time. The kind of blaze that echoes. You might be surprised to know that not all gamma-ray bursts are the same. Some last just a fraction of a second. Others stretch out for minutes. These differences matter. Short bursts quick. Intense flashes are usually the result of two dense objects colliding. Neutron stars slamming into each other in a moment so intense it bends space itself. Long bursts, on the other hand, often come from collapsing giants, a final breath that punches through the cosmos. Let's move toward one of each. Over here, feel how the stars grow sparse? We're in a region where two neutron stars have been dancing for eons. Their orbit is so tight now that they spiral inward faster with every passing second. Watch closely. That last moment, it's like a silent exhale. No warning, no build-up, just one sudden brilliant flash, and then gone. Short bursts like these don't last long enough to show off. But they're loud in their own way. They tell us something special is happening, something ancient and final. Now let's drift toward the site of a long burst. This time, it's slower. You can almost feel the tension building. The star is massive, it's lived a life far larger than most. And as its core collapses, the energy focuses, twists, and fires out like a blade of pure radiation. The beam is narrow, but if you're in its path, you'll know. For a few seconds, the universe feels smaller, focused, like it all comes down to this single, blinding line. And then, once more, it fades. Back in the quiet, you might wonder, why are these beams so narrow? Why don't they shine in all directions? That's the strange thing. It's not just light being released. It's light being funneled, channeled, blasted through magnetic fields, so intense they carve the energy into a tight, focused jet, like shining a flashlight through a tunnel. Only this flashlight burns hotter than anything else the universe has ever produced. And it's not just the energy that travels, it's the information. When those gamma rays hit our detectors, they carry secrets about the star that made them, the space they passed through, and even the age of the universe when they began their journey. Let that sink in. Every gamma-ray burst is a time capsule. Imagine catching a burst that left its star 12 billion years ago. That means you're seeing an event that happened when the universe was only a tenth of its current age. Earth didn't exist. The Milky Way was still forming, and yet, that light has traveled the full span of time and space just to arrive here, just to brush across your mind, across this moment. That's not just astronomy, that's poetry. Now come with me, slowly. Let's glide away from the bright galaxies and into the dark spaces between them, the intergalactic void. It's quieter here. The stars are fewer, but no less important. In these lonely regions, some gamma-ray bursts still happen. They tell us that not all drama requires an audience. Some stars live and die in solitude. They burn just as brightly, even if no planets orbit them, even if no one's there to see. Let's pause for a second. Let the silence stretch. Out here, the distances are so vast that time feels slower. You and I could sit here for 1,000 years, and nothing would change until suddenly, everything does. A burst could appear, lighting up a galaxy we didn't even see before. And just like that, the darkness becomes a stage. That's the rhythm of the universe. Quiet, quiet explosion, then quiet again. You might be wondering how scientists tell how far away a gamma-ray burst is. After all, we can't just measure it with a ruler. We use redshift, a change in the light caused by the expansion of the universe. The farther the burst, the more stretched its light becomes. It's like listening to a siren as it drives away. The pitch drops, the sound fades, and you know it's moving farther and farther. Space does the same thing with light. So when we study a gamma-ray burst, we're not just watching a show, we're reading a message coded in energy, time, and motion. Every flicker tells a story about distance, about age, about the building blocks of matter itself. Let's look at another one now. This one happened in a starburst galaxy, a galaxy that's busy making new stars at a wild pace. The air here, if you can call it that, is thick with gas and light. Stars are being born every second, but in the middle of all this life, one massive star has reached its end. Its core collapses, The outer layers fall inward, then rebound. A jet forms. And in less than 10 seconds, the burst begins. It's long, it's bright, and it carries with it the fingerprints of the star that made it, the types of atoms present, the structure of the dust, the angle of the beam, everything. Scientists race to study it. Telescopes on the ground spin to face the signal. Spacecraft adjust their sensors. In labs and observatories around the world, people stop what they're doing. All for 10 seconds of light. That's how powerful these bursts are. They command attention. And it's not just astronomers. Physicists, chemists, even philosophers lean in. Because gamma-ray bursts aren't just astrophysical events. They're windows into the nature of reality itself. Think about it. These bursts show us how stars die, but they also show us how matter behaves under the most extreme conditions. They help us understand gravity, magnetism, even the limits of time. They are natural laboratories, scattered across the sky. And yet, for all we've learned, there's still mystery. Some bursts defy explanation. Their light curves are strange. Their energy levels are off the charts. Some don't fit into the neat categories we've built. They hint at new physics, new forces, maybe even new types of objects. So every time we see a gamma-ray burst, we ask the same question: what are we missing? That's the heart of science. Not answers, curiosity. Now float with me one more time, back to the edge of a quiet galaxy, where a faint, ancient burst is just beginning to glow. This one is subtle, not as bright as the others, but no less important. Its signal is clean, its energy sharp. And it reminds us of something we often forget, that even the most powerful things in the universe can begin in silence, in patience, in the quiet folding of a star that once burned bright. And as the beam stretches across time, it joins the others, a web of light and memory threading through the universe, each one telling a story, each one waiting for someone to notice. And we did. We noticed. So here we are, floating just above the remains of a star that once ruled this corner of its galaxy. You can still feel the echoes of its life, faint warmth drifting like smoke through space, the soft pressure of particles settling into new patterns. Everything that star ever was has been sent outward, like pages torn from a book and scattered into the wind. Some of those pages will never land. They'll just keep drifting, unbound and unseen, for eternity. But some will find a place. Reach out with me. Let your fingers trail through the dust. This isn't just debris, it's potential. What we're touching is the beginning of something else. Carbon, iron, oxygen. The ingredients of planets, oceans, clouds, trees, and, eventually, people. In a strange, beautiful way, this violent end we just witnessed is also an act of creation. It's the spark that makes everything else possible. You and I, we're not separate from this. We're not outside observers. The iron in your blood, the calcium in your bones, all of it came from stars like this. Not exactly this one, of course, but its distant, ancient cousins. Billions of years ago, a gamma-ray burst scattered the seeds of life across a galaxy. Some of those seeds landed here. Some ended up in you. It's strange, isn't it? To think that light we can't even see, gamma rays flying faster than thought, stronger than fire, played a quiet part in your existence, in mine, in this moment, right now. Let's drift closer to the trail of that burst. It's fading quickly, but we're fast. Not in a rush, just steady, peaceful, like a boat gliding across a quiet lake after the storm has passed. The trail glows faintly, not with light we can see, but with signals we can feel. The space is charged, not dangerous, just aware, the way a room feels just after something important has happened. The universe remembers. Listen carefully. Can you hear it? There's no sound, not really, but there's presence, a subtle hum of memory. The gamma-ray burst didn't just pass through this space, it left something behind. It rearranged molecules. It shifted the spin of particles. It told this region, in the only language the universe speaks, that something remarkable just occurred. And what's more, this isn't rare. Not entirely. Gamma-ray bursts happen somewhere in the observable universe almost every single day. Most we don't see. But a few, the lucky few, happen to point directly at us. And when they do, we get a window. Not just into the death of a star, but into the life of the cosmos. Let's float above a young galaxy now. This one's still forming. The stars inside it are restless, hot, full of fire. Some won't last long. That's the thing about the brightest stars, they burn through their lives quickly. Intense, glorious, short. They live fast. And when they die with drama. There's one now. It doesn't look like much, just a slightly larger, slightly bluer dot in the distance. But that star has a secret. Inside it, pressure is building. Its core has been fusing atoms together for millions of years. Hydrogen into helium, helium into carbon. And now, that chain is breaking down. The balance is tipping. The collapse begins. Not slow, not gentle, sudden. In the space of a breath, the core falls in on itself. Layers slam inward. And then, in two narrow jets bursting from its poles, the energy escapes. Focused. Pure. Relentless. A gamma-ray burst. We watch it from a safe distance, of course. Safe enough to admire the beauty without risking our lives. The beam slices across the galaxy. For a few seconds, that single burst releases more energy than the entire Milky Way does in years. And then, just like that, it's gone. Not erased, just complete. But what comes next? That's where things get interesting. Because after the flash, the real work begins. That star's remains collapse even further, deeper, until gravity wins completely. And at the center of that collapse, at the absolute core of what used to be a sun, something new is born. A black hole. It doesn't glow. It doesn't spin. At least not in any way we can see. It just exists. A point in space where the laws of physics start to blur. A place where time slows and direction loses meaning. The gamma-ray burst was the birth cry. The black hole is the child. Now let's float near it. Not too close. You'll notice the space around it isn't empty. Gas, dust, and starlight all bend toward it, swirling in slow spirals like water circling a drain. The black hole drinks in the leftovers, but not without a little resistance. As material falls, it heats up, glows, screams silently. And sometimes, if conditions are just right, another jet forms smaller, tighter, but still powerful. This is where gamma-ray bursts can teach us more than we thought possible. Because when we look closely at them, at their light, their shape, their behavior, we learn not just about stars, but about gravity, about space-time, about the very structure of reality. Let's zoom out a little. Now we're looking at hundreds of galaxies at once, each one with billions of stars, each one a swirling storm of potential. Somewhere in that sea, another burst is already forming, and another, and another. We'll never see them all. But knowing they're out there, that these events keep happening, reminds us that the universe is still writing its story, and we are still learning how to read it. Even now, with all our instruments, all our models, there's so much we don't know. Why do some bursts last longer than expected? Why do some fade quickly, while others leave glowing trails for days? Are we seeing the full picture, or just the parts pointed at us? Every new burst brings more questions, and that's the beauty of it. We are explorers, not just of space, but of understanding, of wonder, of the invisible, untouchable fabric that connects stars and atoms and minds. We're still hovering in that great stretch of sky, surrounded by 100,000 galaxies, each one spinning quietly. Some are young and blue, flickering with newborn stars. Others are ancient and red, their light stretched thin with time. But no matter the age or the shape, each of these galaxies has likely seen its share of gamma-ray bursts, flashes so powerful they mark the timeline of the cosmos like exclamation points in a long unfolding sentence. Look to your left, just over that cloud of interstellar dust, a small spiral galaxy, barely visible unless you're paying attention. Inside, a long burst just happened, and its afterglow is slowly fading into the dark. We've arrived just in time to watch the remnants dance. Let your eyes adjust. There's a shimmer, faint but steady, like moonlight on water. That glow? It's not just leftover light. It's the universe trying to balance itself again. The space where that star once lived is now expanding, a bubble of particles and waves pushing gently outward into the cosmic sea. You might feel it, the subtle tug of momentum, the way the burst pushed against its surroundings. Like a ripple from a stone dropped in a quiet pond, the energy continues, echoing in all directions. Each atom it brushes, each molecule it touches, now carries the story forward. The story of a life that ended not with silence, but with brilliance. Let's move closer, slowly. You'll notice the colors changing as we approach, not vivid like a rainbow, but delicate, tinted in invisible shades. Infrared, ultraviolet, X-ray, radio, a whole language of light our eyes can't see but our instruments can, and through them we listen. We listen to the patterns in the afterglow, the slight waver in brightness, the flicker of polarization. The way the energy fades tells us something. Like footprints in the snow, the trail leads backward. Back to the star, back to the collapse, back to the moment the universe held its breath. Now imagine just for a second standing on a distant, rocky moon in a far-off solar system. The sky overhead is full of stars, but one is different. For a few brief moments, it outshines them all. Not because it's closer, not because it's brighter by nature, but because it just released more energy than anything else in the visible universe. From that moon, you wouldn't know the details. You wouldn't see the jet, or the magnetic fields, or the core collapse. You'd just see a light that wasn't there before, a light that leaves you wondering. And maybe that's what makes gamma-ray bursts so powerful, not just their energy, but the mystery they carry. They don't ask for attention, they don't last long, but they demand awe. Let's return now to open space. Let the dark surround us again. Feel how soft and still it is out here. There's no wind, no up or down, no sound but the rhythm of your own thoughts. It's easy to forget how much is happening all around us, just out of view. Far ahead, another gamma-ray burst is about to begin. This one's different. It's from a type of star we rarely see, a blue supergiant, one of the most massive and short-lived stars in existence. These stars burn brightly, live fast, and end dramatically, and this one is nearing its final moment. Watch carefully. The outer layers of the star are beginning to bulge. Pressure is building at the core. It's like watching a balloon tighten before it pops. Only this balloon is bigger than our entire solar system, and its pop will echo through billions of light years. The collapse starts inward first, then outward in fury. Two jets form instantly, blasting through the outer layers like drills, and then the flash. This burst is longer, thicker, rich with energy. It sends gamma rays slicing through space with the sharpness of a blade. They pass through gas clouds, skip off the edges of distant solar systems, skim across frozen comets sleeping between stars. You and I float nearby, not near enough to be harmed, but close enough to see the structure. There's elegance in the violence. The jets don't wobble. They're focused, precise. And within them, new particles form, not by chance, but by necessity. Matter is being made and destroyed in the same breath. Now turn your gaze slightly just beyond the beam's edge. You'll see dust grains glowing faintly. The burst has heated them. Some will crumble, some will change, and some will merge, stick together, and begin the slow process of becoming something new. This is how galaxies evolve, not just through peaceful accumulation, but through dramatic reshaping. One gamma-ray burst can carve out a bubble in the gas clouds, making space for stars to form. Or it can send shockwaves that cause nearby clouds to collapse, sparking new life. One ending triggers many beginnings. And if you listen, really listen, you can almost hear the crackle of creation. Let's drift down, toward a small clump of dust and gas lit faintly by the burst's wake. Inside, particles are beginning to gather. They don't know it yet, but they're forming the early skeleton of a star. One day, it will shine. Maybe it will have planets. Maybe it will be watched from afar by minds like ours. Or maybe it will burn alone, silent and unseen. Either way, it started here in the path of a dying star's final breath. We float farther now, letting the afterglow fade behind us. Space stretches ahead like a calm ocean at night. The stars are distant, faint, the kind of light you can almost feel more than see. Somewhere out there, new bursts are waiting to begin. Others are already on their way toward us, their light still traveling, still trying to reach this quiet corner of the galaxy we call home. And you are here for it. You are present, alive, and listening, floating gently in a sea of dark and fire and memory. The universe doesn't know we're here, but we do, and in this shared stillness, that's more than enough. As we move gently through this dark patch of space, following the faint trail of the last gamma-ray burst, something starts to become clear. These bursts, they're not just single events. They're part of a larger process, a rhythm, a pattern that the universe has followed for billions of years. In the same way that seasons change or waves crash on shores, these colossal explosions are woven into the natural order of things. They're unpredictable, yes, but not random. There's a logic hidden behind the fire. Take this region of space just ahead. A little colder, a little quieter. Not much going on here, it seems. But if you could rewind time not by years, but by hundreds of millions, you'd see something different. You'd see a star, enormous and fast spinning, surrounded by a disk of swirling gas. One of the key suspects behind many long gamma-ray bursts is a type of star called a Wolf-Rayet star. Now, that name might sound gentle like a forest creature, but trust me, these stars are anything but. Wolf-Rayet stars are old and stripped down. They've lost their outer hydrogen shells and are burning hot at their cores, spewing out winds faster than anything you've felt before. They can be over 20 times the mass of our sun, but they don't live long. They don't get to grow old and quiet. Instead, they go out in a flash, literally. And sometimes, when the conditions are just right, when the rotation is fast, the mass is high, and the magnetic fields are aligned, a gamma-ray burst is born. It's not guaranteed. Even stars this massive don't always burst. Most just collapse into black holes with a sigh. But a few, a rare violent few, light up the sky with beams of gamma light that cross the universe. And here's something incredible. Some of the longest gamma-ray bursts on record have lasted nearly 1,000 seconds. Imagine that a beam of the most powerful energy in existence shining for over 16 minutes. That's enough time to make a cup of tea, sit down, and still be staring at the brightest light the cosmos has to offer. Think about what that means. A single event, brighter than everything else in its galaxy combined, lasting long enough for us to not only detect it, but to observe its evolution in real time. Let's float toward one of those long-duration bursts. You can almost see the timeline stretched out ahead of you, the build-up, the flash, the decay. As we get closer, the light sharpens. You might feel the data pressing in wave after wave of high-energy photons racing past. That's what our space telescopes catch. Not just light, but time, speed, direction. Every photon tells a piece of the story, and when we catch enough of them, we can reconstruct the moment almost perfectly. Now look to your right, there's a small satellite, drifting steadily through orbit. It's not flashy, just a metal box with sensors and antennas. But this humble machine might be one of the first to detect a gamma-ray burst. Instruments like NASA's Swift or Fermi spacecraft are trained on the sky at all times, watching for the telltale flash. When they see one, they alert the entire world in seconds. Astronomers everywhere scramble to point their telescopes at the sky, both on Earth and in space, to catch the afterglow before it fades. And that brings us to a wonderful truth. Even though these bursts happen so far away, so impossibly distant, they pull people together here on Earth. Scientists in different countries, using different tools, speaking different languages, all working to understand a single flash that might last only a few moments. That's how powerful gamma-ray bursts are. They're not just physical events, they're moments of unity. Now drift with me deeper into the early universe back in time. The farther we go, the younger everything looks. Stars are just beginning to form, galaxies are clumping together like drops of ink in water. And even here, even this early, we find gamma-ray bursts. That's how we know they've been happening for most of cosmic history. In fact, the most distant gamma-ray burst ever detected came from over 13 billion light-years away. It happened when the universe was less than 5% of its current age. That light traveled across time itself through empty space, past countless galaxies, dodging dust and gas and gravity wells just to reach us. And we saw it, we caught it, a flicker from the dawn of time. But gamma-ray bursts don't just tell us about stars, they tell us about the universe's expansion. You see, because their light has to travel so far, it gets stretched. This is called redshift. The farther away the burst, the more its light is shifted toward the red end of the spectrum. By measuring that redshift, we don't just learn how far away the burst is, we also learn how fast the universe is expanding. These flashes help us measure the very fabric of the cosmos. And speaking of expansion, did you know that some scientists have proposed using gamma-ray bursts as cosmic distance markers? Like mileposts on a highway, only the highway is space. and the mileposts are explosions from the deaths of stars. If we can understand how much light is released in a burst, and compare it to how much we receive, we can estimate how far away it was. The more we refine that method, the better we can map the shape and speed of the universe. Let's turn now toward a region of space where something rare is unfolding. Two neutron stars, impossibly dense, city-sized remnants of old supernovae, have been spiraling toward each other for millions of years. Each one weighs more than our Sun, but is only about 12 miles across. That's like fitting a star into the size of a city block. And now they're touching. Watch closely. The collision takes only milliseconds, but the result is staggering. In that instant, a huge amount of mass is converted into energy. A flash erupts brief, intense, a short gamma-ray burst. This is different from the long bursts we've seen before. Short bursts are sharp. They're like a cosmic blink, but they're no less powerful. In fact, some of the heaviest elements in the universe, gold, platinum, uranium, are formed in the aftermath of these collisions. So the ring on your finger, the circuitry in your computer, the metal in a spacecraft, it might all come from an ancient neutron star merger. That's not just poetic, it's real. And in that merger, gravitational waves also ripple outward. That's right, not just light, but waves in space-time itself. We can now detect those waves with observatories like LIGO and Virgo. When we catch both the light of a gamma-ray burst and the ripple of a gravitational wave from the same event, it's like hearing and seeing the same moment in stereo. It's a cosmic duet. And it gives us more information than ever before. We're still gliding, unhurried, just past the edge of that neutron star collision. The dust is still settling, particles curling into new shapes, some too small to name. But let's drift away now. Let's leave that story behind and aim ourselves towards something even stranger, something almost no one ever talks about. Picture this. You're floating through deep intergalactic space, not between stars, between galaxies. The black here is thicker, older. It's the kind of quiet that makes you feel like even light might get lost. But ahead, there's a pinpoint, not a star, a burst, tiny, focused, flickering like a distant match head in a cave. This is something rare, a possible orphan afterglow, a gamma-ray burst that didn't point its beam at us, but left behind an echo of light we just happened to stumble across. Most GRBs fire their beams in very narrow cones, imagine them like laser pointers. If that beam isn't aimed directly at us, we don't see the burst itself. But sometimes, just sometimes, we catch the faint afterglow around the edges, days or even weeks later. It's like hearing a whisper through a closed door and knowing something dramatic happened inside. Now come closer. Watch the faint shimmer trail away into the dark. That's the residual X-ray glow. It fades slowly, like the warmth left on your skin after the sun sets. That glow helps astronomers confirm where the burst came from, even if we missed the flash itself, and it helps fill in gaps, gives us a more complete picture of how often these events occur. You see, the gamma-ray bursts we do see, they're only a tiny fraction of what actually happens. Maybe just 1% of all bursts are aimed our way. That means that for every one flash we record, there could be 100 others scattered across the sky, invisible to us. Just think the night sky could be filled with the fading memories of explosions we never saw. And speaking of invisible, let's talk about dark GRBs. Not all bursts leave behind a visible glow. Some just vanish. We detect the gamma rays, but when telescopes swing to follow up, there's nothing there. No X-ray, no optical light, no trace. These are called dark bursts, and they're one of the most intriguing mysteries in gamma-ray research. Are they hiding behind thick clouds of dust? Are they happening in galaxies too faint to see? Or are they something else entirely? Let's explore one. There's a whisper in the data, a burst recorded last year. The gamma rays came in strong, sharp, clear, but when dozens of telescopes searched the sky, they found only empty blackness, no afterglow, no host galaxy, nothing. It's like the burst appeared from a blank page. Now, lean in with me, see that speck? Barely visible, even with enhanced contrast. That might be the source, a galaxy so faint, so far, that its light is drowned out by the dark between stars. We can't know for sure, but it reminds us that we don't see everything. The universe holds its secrets tightly, and gamma-ray bursts are one of its favorite riddles. Here's another one for you. The universe's most energetic explosion ever recorded wasn't a supernova, it was a gamma-ray burst. In 2022, astronomers detected what they called the brightest burst of all time. It came from over 2 billion light-years away and was so powerful it overloaded our instruments. The burst was given a name, GRIB 220, 1009A. Its light lit up Earth's atmosphere in ways we'd never seen. Some of our gamma-ray detectors weren't even built to handle something that strong. It was like aiming a magnifying glass at a firefly and accidentally catching the sun. And yet, even that monstrous burst only lasted a few minutes. That's the thing with GRBs. They don't linger. They roar through space, bend it, break it, and then vanish like dreams before dawn. Let's slow down for a moment. Breathe in with me. Feel how large everything is around you. The silence here isn't empty. It's filled with potential. Somewhere right now, in a galaxy we've never seen, a star is beginning its final spin. A jet of light is building. The core is collapsing. And in just a few more moments, another gamma-ray burst will fire into the dark. And we might never see it. But the universe remembers. Let's glide toward the site of a very old burst. Not one we saw in real time, but one whose echo we found in a fossil. That's right, Earth itself holds the fingerprint of a gamma-ray burst in its bones. Roughly 450 million years ago, during the late Ordovician period, something happened to Earth's atmosphere. Scientists studying mass extinction events noticed signs of rapid ozone depletion. The cause? One possibility is a nearby gamma-ray burst. Maybe not dangerously close, but close enough. The burst could have bathed Earth in high-energy radiation, stripping away part of the ozone layer and exposing life to harmful ultraviolet rays. That's the power these bursts have. Even if they're hundreds of light-years away, they can still leave marks not just in the sky, but in the fossil record, in stone, in ice, in the deep memory of our planet. Now feel the chill around you. We've drifted into a cold patch of space, not empty, but filled with relics. Ancient photons from long-dead bursts still pass through here. We don't notice them on Earth, but they're there. Every second, hundreds of high-energy gamma-ray photons are slipping past your body. Not dangerous, they're too scattered, too diluted. But they're the echoes of unimaginable violence, passing through us like breeze through leaves. And here's another thing. GRIBs are helping us solve one of the biggest mysteries in cosmology, how stars formed in the early universe. Because GRBs are so bright, we can use them like cosmic lighthouses. When one occurs in a distant galaxy, its light shines through the space between galaxies, illuminating the gas and dust along the way. By studying how that light changes what it absorbs, what it leaves behind, we can map the structure of the early cosmos. It's like lighting a match inside a cave and seeing the walls for the first time. They don't just light up space, they light up time. You might be floating here with me now, wondering, how could something so brief, so rare, so violent, also be this beautiful? That's the paradox of gamma-ray bursts. They are both ends and beginnings. They erase and they reveal. They destroy and they illuminate. And we're lucky enough to witness them. Let's stay floating in this quiet corridor between galaxies just a little longer. It's colder here, more isolated. The light from the last burst has faded completely now, like a distant memory slipping out of reach. But don't let the silence fool you. The dark isn't empty. It's alive with things we can't see, and some we haven't even imagined yet. You know, gamma-ray bursts don't just reveal the stars that make them sometimes, they reveal things we didn't even know were there. Picture a gamma-ray beam slicing through a galaxy, its light passing through clouds of gas, through dust lanes, through filaments of invisible matter. As that light reaches us, its change slightly dimmed in some places, stretched in others. Those changes act like fingerprints. They tell us what the light passed through on its journey. And sometimes, that journey includes something odd. In 2013, a burst's light revealed a surprising amount of gas in a region of space we thought was empty, a place where no galaxies had been seen. But there it was, absorption lines in the spectrum, a silent record of something invisible. The burst had lit up a hidden structure, maybe a rogue gas cloud, maybe a piece of the cosmic web. It was like a flashlight catching the edge of a door we didn't know existed. And that's the thing, gamma-ray bursts don't just tell us about themselves. They act like sudden flashes of lightning that reveal the landscape for a split second. Mountains, trees, caves, things that otherwise sit in total darkness. Every burst lights up part of the unknown. Now let's shift direction. Gently rotate with me. Feel how the stars spin around us as we turn. Ahead lies a region of space where we've started to find clues not just about how stars die, but about what kind of life can exist around them. It might seem strange, talking about life after all this cosmic violence, but here's something astonishing. Not all gamma-ray bursts happen far away. In fact, some of them might be happening in galaxies a lot like ours, and that raises a chilling question. What would happen if one occurred nearby? The answer depends on distance. If a gamma-ray burst occurred within a few thousand light-years and was aimed directly at Earth, it could, theoretically, cause severe damage to our atmosphere. It wouldn't blow up the planet or anything like that, but it could tear apart molecules in our upper atmosphere, strip away the ozone layer, and expose the surface to harmful radiation. Some scientists believe that mass extinctions in Earth's past, including the one we touched on earlier, may have been triggered this way, not by impact, not by volcanoes, but by light, a beam of energy from a dying star, arriving after millions of years of travel and altering the course of life with a single flash. But here's the comfort. Space is huge, and bursts are rare. The odds are astonishingly small, so small that they feel more like ancient myths than real threats. Still, it's humbling to know we live in a cosmos that sometimes writes endings with beams of light. Let's look at something more hopeful now. Drift with me toward that faint blue patch just beyond the cluster of galaxies. That's a star-forming region, a stellar nursery. In places like this, the dust left behind by long-dead stars begins to clump, pulled together by gravity, warmed by friction, until something new is born. A protostar, maybe more than one. Now imagine that one of those stars is massive, bigger than most. You can already tell its light is bluer, its winds stronger, its future shorter. It will likely die in a gamma-ray burst. But here's the twist. It might also have planets. That's something we've only just begun to study. Massive stars don't often keep planets for long. Their intense radiation and stellar winds usually blast nearby material away. But what if a planet managed to survive? Orbiting far enough to stay cool, but close enough to be warmed by its star's fierce light. We don't know if life could form there, but we do know this. If it did, it would be life that evolved in the shadow of potential catastrophe. Every sunrise would be a reminder of the star's power. Every night sky would be filled with the pulsing warnings of nearby stellar deaths. Could such life evolve differently? Would it be more resilient? Would it watch the stars with reverence or fear? And if that gamma-ray burst finally came, that life might never even see it. The burst would arrive in seconds, faster than thought, faster than sound, faster than memory. It would be history written in one brief blaze. But maybe, just maybe, that life would have already launched something into orbit. A probe, a telescope, a signal. And long after its world was gone, the echo of its curiosity would still float through space, crossing paths with bursts, comets, and dust. Just like ours. Because we're doing the same thing. Every telescope we build, every satellite we launch, is part of a larger act of remembering. We're trying to preserve wonder, trying to witness the beauty of the universe, even when that beauty arrives wrapped in danger. And that's why gamma-ray bursts matter so much. Not just for the science, not just for the facts, but because they remind us what it means to look up, to be small, yes, but also to be brave, to be curious. Now take a moment, look back behind us, all the bursts we've passed, the stars we've watched die, the afterglows we followed across space, they're still out there, still shining, even if we've moved on. They don't need us to remember them, but we do, because remembering is how we stay connected to something bigger than ourselves. There's a glow ahead, soft, pearly, shifting. It doesn't pulse like a star, and it doesn't shine like a galaxy. It hovers, faint, suspended like a breath between heartbeats. We drift toward it, not sure what it is yet. It's not a gamma-ray burst, not exactly, but it might be what's left after one, or what's waiting before the next. A transitional space, a memory in the making. Scientists sometimes talk about a thing called a magnetar. It sounds like something from a comic book, but it's real and strange. Stranger than neutron stars. stranger even than black holes, in some ways. Magnetars are formed when certain stars collapse, but instead of becoming black holes, their cores are compressed into ultra-dense balls with magnetic fields, so intense they could strip the data from a credit card from halfway to the moon. And sometimes, just sometimes, magnetars might produce gamma-ray bursts of their own. Short ones, violent, confusing. Imagine standing on the surface of a moon orbiting a magnetar. You'd be crushed by gravity, of course, but let's pretend we're safe, invisible, untouchable. What would you see? The sky would ripple with magnetic storms. Invisible arcs of power would swirl above your head. The magnetar wouldn't glow like a sun, it would spark, twitch, flare, and if it erupted, it might release more energy in a fraction of a second than our sun will emit in 100,000 years. Some researchers believe that a handful of the short GRBs we've seen may have come not from neutron star mergers, but from magnetar flares, especially the soft gamma repeaters. These flares repeat, unlike most bursts. They flash, dim, then flash again. They're not explosions, they're convulsions. We don't fully understand them yet, but they might help explain some of the missing bursts, the ones we detect without warning and can't quite categorize, like whispers in a language we haven't learned to speak. Let's hover near one now. Feel that? The air around it is sharp, not hot sharp, like standing beside an invisible wire charged with electricity. It hums with tension. The magnetism presses against space itself. You wouldn't feel it on your skin, you'd feel it in your mind, like something tugging at the thoughts just behind your eyes. Then snap. A burst, tiny, measured in milliseconds. Not enough to light a galaxy, not enough to ripple the interstellar dust, but enough to be seen across the cosmos, enough to matter, to signal that even small things, compact things, hidden things, can reshape their surroundings. Now let's float up and away. Higher now, faster. We're leaving behind the realm of visible galaxies. Ahead lies the large-scale structure of the universe, the cosmic web. Vast filaments of dark matter and gas, stretching like veins through space. This is the skeleton of the cosmos. And even here, gamma-ray bursts have stories to tell. You see, when we catch a burst at a great distance, its light doesn't just tell us about the star. It tells us about everything the light passed through, including the filaments of hydrogen gas that make up the intergalactic medium. That's not just poetic, it's measurable. We can analyze the absorption lines in the burst's afterglow to detect the shadows of gas clouds billions of light-years away. These clouds don't glow on their own, but when light from a gamma-ray burst passes through them, they reveal themselves. In this way, gamma-ray bursts have become a tool not just for studying stars, but for studying the invisible structure that binds the universe together. We're using explosions to see silence. And here's something almost no one talks about. There's a chance, a small one, but real, that gamma-ray bursts could help us find signs of civilizations beyond Earth. Now, this isn't about aliens launching gamma-ray weapons into space. It's subtler than that. You see, some scientists have proposed that the dangerous effects of gamma-ray bursts could be a bottleneck in the development of life. If a planet is too close to a frequent burst source, life might never evolve past the microbial stage. Too many mass extinctions, too much instability. So maybe, just maybe, intelligent life only arises in certain safe zones, areas of galaxies where bursts are rare. If that's true, then the distribution of gamma-ray bursts might help us narrow down the most likely places to find other civilizations, places tucked away from the danger, sheltered. And here's the twist. We are in one of those safe zones. Our solar system is on the calm edge of a spiral arm, far from the wild star-forming regions. Our sun is modest. Our neighborhood is quiet. It's as if we evolved in the lull between firestorms, a quiet pocket in a violent galaxy. That realization doesn't frighten me. It fills me with wonder. Because it means we were lucky. Not just lucky to exist, but lucky to exist now, in a moment when we have the tools to see, to study, to understand these great cosmic flashes. If we'd lived just 1,000 years ago, we might have missed it all. The bursts would still happen, but we'd have no way of knowing. Today, we catch them as they appear. We trace their light across time. And maybe, someday, Another civilization on a far-off world will catch the glow of a burst that happened in our galaxy, maybe even one we recorded. They'll see the same signature. They'll study the same curve, and they'll wonder about us, just as we wonder about them. What we're approaching now isn't a flash in the sky. It's something older, something ancient enough to make light itself feel young. Suspended at the edge of a long, silent collision lies a shape not made of matter, not exactly a distortion, a wound in the fabric of space, blacker than black, no glow, no reflection. Just gravity pressed into a singular, invisible point. But wait, pause here. Do you feel that? A subtle ripple, a faint rhythm, as if space around you were breathing differently. That's no illusion. It's the ghost of something that once was. A stellar collapse so complete, so total, that even time bent to its will. This black hole, quiet now, was once the heart of a gamma-ray burst. The star it came from burned bright, faster than most. It didn't grow old. It didn't fade. It ended the only way it knew how, violently. But the explosion wasn't wide. It was narrow, directed, focused into twin beams of light and force. And in that moment, in that final cry, it became visible across the entire universe. Now, all that's left is this. A silence so deep it draws in starlight. No sound, no heat, just memory. Not all gamma-ray bursts end this way. Some leave behind neutron stars, others leave nothing at all. But when they form black holes, the story becomes stranger. Because now, gravity doesn't just hold matter together, it holds secrets. Whatever happened inside that collapse, we'll never see. Not even light can escape. And yet, we know, because of what it left behind. Instruments on Earth, humble, trembling machines caught the burst. Just a blip on a screen, a reading, a timestamp, but it was enough. Enough to tell us how fast it came, how long it burned, how much energy it gave off in its final breath. It was enough to sketch the death of a star without seeing the body. That's what science becomes out here. Reverence without touch. Float closer now. Do you see that faint blue arc looping around the black? That's gravitational lensing, the light of distant stars bent by the hole's pull. It's not decoration, it's evidence. Space is not static. It stretches, folds, warps, and in these warps, light travels sideways, backward, even in loops. Through this distortion, we glimpse galaxies behind galaxies, light twisted into rings. That same bending of space happens when gamma-ray bursts occur near massive objects. Sometimes, we don't just see one burst. We see echoes, repeated images of the same flash, arriving seconds or minutes apart. The universe, in its vastness, playing tricks with time. Let's leave this place slowly. The dark here has weight. The silence wraps around you like fabric, not cold, but thick. Every movement feels deliberate, even light tiptoes. But ahead, something changes. There's a field of gas, massive, shimmering like fog under moonlight, and embedded within it a dying galaxy. Its arms are warped, its core fractured. This galaxy once had hundreds of bursts, maybe more, but the stars here are old now, heavy, full of metal. Their time is short. Gamma-ray bursts rarely happen in old galaxies like this. Most come from young, chaotic places. But sometimes, in the quiet after the storm, one last burst breaks through, a final fire in the ruins. We're witnessing that now. The burst itself is gone, but its fingerprint remains. The gas it tore through still glows. Its pressure waves still echo in the dust. And something new has formed at the edge, a knot. A dense clump of matter that didn't exist before the burst. It's not alive. Not yet. But it will be. Given time, it will collapse into a star. The irony is sharp. From the death of one star, another is born. The burst that destroyed becomes the spark that creates. This is not philosophy. This is physics. Let your gaze move downward. Do you see the tiny fractures in the gas? That's turbulence caused by shock waves. Each one traces back to the original jet. And nestled between them are trails of ionized atoms, molecules stripped bare, wandering like exiles through the cloud. When they cool, they'll bond again. First into hydrogen, then into something more complex. Eventually, if the conditions are right, into amino acids, the raw ingredients of life. You're looking at a chemistry lab built by destruction. But the most delicate thing here isn't the gas, it's time. The burst happened 8 billion years ago, half the age of the universe, but the light and the changes it caused are only now reaching us. That delay means we're always looking backward, observing endings long after they've occurred, but that also means our own light is just beginning to travel. Imagine that. The machines we build, the signals we send, the echoes of our own stars all drifting outward, past the places where gamma-ray bursts once bloomed. Our technology is young, our story just beginning. But in 100 million years, something might look toward the Milky Way and see a ripple, a whisper of life among the arms of a modest spiral galaxy. And perhaps they'll wonder, the way we do now, what happened there? Further ahead, just beyond the curling edge of that luminous gas field, the stars begin to thin. Fewer now, not because they've burned out, but because this part of the cosmos was always quieter. Less crowded. The galaxies here are spread wide, lonely islands across a dark ocean. These are the cosmic outskirts where gravity takes its time and light travels in longer strides. And it's here, in this subtle emptiness, that we find something unexpected. A gamma-ray burst with no obvious source. No bright host galaxy, no surrounding cluster, just a pinpoint of high-energy light, seemingly suspended in the void. It flared once, briefly, then faded. Telescopes scoured the region for weeks, searching for the faint glow of a host, a dwarf galaxy, a satellite system, even a wandering star. Nothing. It was like watching a lightning strike from a cloudless sky. These bursts are rare, we call them hostless. But they're not truly alone. They might come from stars that were ejected from their galaxies long ago, flinging through intergalactic space for millions of years, dragging a halo of gas behind them, until finally, quietly, they die. Imagine that journey. A star, born in the dense heart of a spiral arm, pulled from its home by gravitational tides, cast out, slow at first, then faster. It drifts for eons through silence, through the unseen winds between galaxies before finally collapsing in a distant place, far from everything it once knew. And when it dies, the burst escapes in all directions. Most of it vanishes into the dark, but a tiny sliver finds us, crosses the deep, the long cold, and brushes the lens of a detector perched high above Earth. It's poetic in a way that feels unfair. The star's final act, its only chance to be remembered, happens light years from where it was born, and we only see it by accident. But that's what makes it beautiful. Not planned, not expected, just real. We drift closer to the coordinates. There's no trail here, no afterglow, just the thinnest smear of gas, still rippling from the burst's brief fury. It's like the imprint of heat on a bedsheet after someone's left, faint, fading, but there. And it tells us something crucial. Not all gamma-ray bursts need the comfort of galaxies. Not all need dense stellar nurseries or rich, crowded neighborhoods. Some stars live and die alone, and yet their deaths shape space just the same. Pull back now. Look around. All across the sky, these flashes are happening. Not every day, not every hour, but constantly, quietly. The universe is peppered with afterglows. Some just ended. Some began before Earth was a planet, and some, the most ancient ones, are still on their way. Their light hasn't reached us yet. But it will. Now, turn slowly. Behind us there's a new pulse. Very faint, too weak to trigger an alarm, but enough to catch the edge of a wide-field survey instrument, one of those automated eyes, pointed always at the sky, watching, recording, never blinking. This one's strange. Its spectrum is off. The light is slightly curved, twisted. Some researchers think it could be an example of a gravitationally lensed burst, a flash of light that passed near a massive cluster of galaxies and got bent, magnified, and stretched. So we're not just seeing the burst, we're seeing multiple versions of the same burst, arriving at different times. Imagine watching the same star die twice, from different angles, days or weeks apart. That's not science fiction, that's happening. The light around us now has been folded by space itself. It wrapped around invisible masses, bent through the hollows of gravity. It's the same burst, arriving in layers. First the brightest core, then the outer ring, then the dimmest echoes, and each one tells us something new. Not just about the burst, but about what the light had to pass through to get here. We can measure the delay between the flashes, use it to map the mass of galaxies we can't even see, use it to study the shape of dark matter, even test our theories of how space expands. One burst, 1,000 answers. We hover inside this lensing field for a while, letting the layers pass over us like waves. You might even feel it the way time stretches here. It's not disorienting, just slow, like watching rainfall in reverse. Then the light fades, and we drift forward again, pulled not by force but by curiosity. There's a region ahead where the cosmic microwave background, the oldest light in the universe, brushes up against a massive, chaotic cluster. It's an active region. Star formation here is frenzied. Thousands of new suns born every year, feeding on rivers of gas pulled from neighboring galaxies. And here, naturally, we find the conditions for something even rarer, a population of ultra-long gamma-ray bursts. These are the rarest of the rare. They don't last seconds, they last hours, some maybe even longer. The stars that make them aren't just massive, they're monsters. Possibly blue supergiants, with outer layers that take longer to collapse, longer to burn through, longer to release the full fury of their deaths. We've only recorded a few. They're hard to catch. Their duration makes them difficult to distinguish from other slow events. Active galactic nuclei, tidal disruptions, flaring quasars. But when we do confirm them, they change everything, because they suggest there are more ways to die than we thought, more paths a star can take before its last breath, more variations in the final flare. It's like hearing a familiar song, but in a completely new key. You and I are watching one now. It's already been going for 45 minutes. The central jet is stable, steady, not a flash, but a burn, a beacon. From our perspective, it's elegant, controlled. But inside that star, chaos, rotating plasma, magnetic fields twisting like ropes, matter folding in on itself faster than physics once thought possible. Somewhere in that storm, a black hole is forming, slowly, methodically. This isn't a scream. It's a deep, long sigh. And when it ends finally, when it ends, the galaxy around it will shimmer with aftershocks. Gas clouds will ignite, particles will scatter, and someone, somewhere, will write down the moment. We've left the ultra-long burst behind now, its afterglow still visible far in the distance, like the last ember of a dying fire. But we're headed elsewhere, because there's something stranger waiting in the shadows ahead. Something most haven't seen, something most haven't even asked about. We're approaching what may be a false burst. Yes, not all gamma-ray bursts are what they seem. Some of the signals we've catalogued, especially in the earlier days of observation, came not from distant galaxies or collapsing stars, but from much closer to home, from our own sun, or from Earth's atmosphere, or from high-energy particles bouncing through our magnetosphere. Imagine watching a monitor. You see the spike, the unmistakable curve, the sudden climb and the sharp drop-off, a burst. You hold your breath. Could it be another ancient death? A star collapsing 1 billion years ago, whispering through the dark? But then, something's off. The timing doesn't match. The direction doesn't align. It wasn't from the sky. It was from the Earth. Sometimes lightning, yes. Lightning creates something similar to a gamma-ray burst. We call them terrestrial gamma-ray flashes. Brief, sharp bursts of high-energy light launched upward from thunderclouds during powerful storms. For just a fraction of a second, the sky above us becomes a source of gamma rays. It's faint, harmless, but real. And the irony is hard to ignore. While we scan the deep, measure the void, and watch for signals from the edges of the observable universe, a storm on our own planet can mimic the voice of a dying star. The cosmos, it seems, has a sense of humor. But let's move beyond our own sky. Let's go farther now, past the glimmering shell of the Milky Way, into the spaces where galaxies are more suggestion than shape, faint spirals smeared across the black like thumbprints on glass. We're heading toward the realm of simulations. Not real stars, not real bursts, but the ones we build in code, in massive servers buried under mountain labs or floating aboard satellites. We create artificial universes and populate them with virtual stars. We tweak variables, mass, spin, composition, and watch what happens when they die. Why? Because gamma-ray bursts are too fast to predict, too bright to fully model, too strange to understand with direct observation alone. So we build digital stars, let them live, let them die, and then compare. And sometimes, something matches. A curve, a pattern, a structure in the jet. And when that happens, we learn. We refine. We take a step closer to knowing not just what these bursts are, but how they came to be. You see, this is one of the quiet truths about science in the space age. It's no longer just telescopes and observatories. It's code. It's models. It's simulations that run for weeks, trying to match a light curve that lasted 3 seconds. And when the match is found, there's silence. The kind of silence that feels like music. Let's move again. There's a soft patch ahead, a region between clusters. The light here is diffused, stretched. Nothing violent has happened in a while. But even here, even in this quiet, the memory of old bursts still lingers. Particles, tiny, high-energy remnants of distant explosions pass through this space constantly. Cosmic rays. Some of them were born in the shock fronts of gamma-ray bursts, accelerated to near light speed, thrown out like seeds into the dark. And they don't stop. Even now, some of those particles are striking Earth's atmosphere. Right now, as you read this, they pass through walls, through oceans, through your own body, harmless, invisible, but present. You've been touched by the remnants of a gamma-ray burst and didn't even know it. The universe doesn't need your permission to include you in its story. And what about the end of that story? What happens when the gamma-ray burst fades? When the light is gone, the particles scattered, the host galaxy dark once more. Often, nothing. There's no monument, no crater, no mark left on the fabric of space. But sometimes, we return years later and we find something new. A remnant, a supernova shell, a dusty ring, a young neutron star spinning in the cold, sending out pulses of radio light like a lighthouse too far from shore. We call these pulsars. And though not all gamma-ray bursts leave one behind, some do. You might be watching one now, see that tight, rhythmic blink? That's a newborn pulsar, formed in the ashes of the burst we saw half a galaxy ago. Its signal is weak, but it's steady. It will keep spinning for millions of years. A ticking clock in a region of space that forgot time. We'll leave it now. There are more places to see, more bursts still glowing. But take that rhythm with you. A reminder, not everything ends in silence. We're entering a galaxy cluster now. Not just one galaxy, but thousands, bound together by gravity, caught in an ancient dance. Some are giant ellipticals, swollen, golden, and tired. Others are spirals like our own, their arms stretched out in long, dreamy curls. Between them lies hot gas, millions of degrees, filling the space between galaxies with a dim, invisible light. And floating through that light? A new gamma-ray burst, caught just minutes ago by a wide-field telescope above Earth. Its coordinates now beam across networks, waking astronomers on every continent. They scramble not in panic, but in reverence. In this field, seconds matter. The sooner you point a telescope at the burst, the more you catch. The earlier you see the afterglow, the better your window into the moment of death. We glide into its path. Not toward the beam that would be suicide, but just beside it, off-axis, far enough to observe. You can already see the fading fire behind the dust, a long burst, likely a massive star collapse. But this one's unusual. Its spectrum carries metal lines. Nickel, iron, cobalt. That means the star wasn't young. It was old, heavy. It lived long enough to build complex elements in its core, the kind that only appear after millions of years of slow, furious fusion. This star had history, and in its death, it has released those elements into space. Some of them will be caught by nearby clouds. Some will form into new stars. Some might drift for 1 billion years before becoming part of a planet, or a cell, or a song. That's what makes gamma-ray bursts more than just explosions. They're delivery systems. They seed galaxies with the elements of life. And there's more. Drift closer, past the central glow. There, in the far edge of the afterglow, something's shifting. A region of polarized light. That's rare. It means the burst jet wasn't chaotic. It was organized, twisted by strong magnetic fields, structured like a spiral or a corkscrew, not a fire hose. That structure is important. It tells us about the mechanism deep inside the dying star, the unseen engine that created the burst. Some theorists believe that inside every long gamma-ray burst lies a rapidly spinning black hole, formed in the collapse, dragging space around it in a storm of energy. Others think it's a magnetar, a neutron star spinning so fast, and with such strong magnetism, that it fires off the burst before it collapses further. We don't know yet. But this polarized light? It's a clue, a piece of the puzzle. It suggests order, purpose, not randomness, and that changes the model. It suggests that a star's death might not be just a collapse, but a transformation, a machine igniting once, perfectly, and then vanishing. Let's move on. Through the dust lanes now, past the shock fronts, and into the soft, neutral regions beyond. Here, we find the edges of other stories' bursts we missed, some too far, some aimed away. Their remnants are harder to spot. No glow, no trails, but if you look close, you'll see the scars. Stripped gas, ionized rings, regions where dust has been heated and pushed away, forming bubbles in the interstellar medium. That's how we know something happened. The absence of dust, the edge of a void, the echo of force. We trace these voids backward, reconstruct the moment, build the profile. Even without the burst itself, we can map its footprint, like detectives at a crime scene where the only witness is light. And light, it turns out, tells the truth. Sometimes, we even find multiple bursts from the same galaxy, not at the same time, not even in the same million years, but recorded, catalogued, stacked. This tells us that gamma-ray bursts don't follow rules. They don't avoid old galaxies. They don't only happen in youth. Sometimes, they return, like thunder rolling through the same valley, separated by epochs. Now we float above a galaxy where that's happened. The first burst came 7 billion years ago. The second, just a billion years after. Different regions, different stars, but the same host. It's a reminder that galaxies are vast, complex, capable of holding both violence and calm, not just over space, but over time. That second burst, we only saw part of it. The beam was angled slightly off. What we caught was the edge, the afterglow, not the fire. But even that was enough. Enough to map the jet's angle. Enough to estimate its energy. Enough to know that something beautiful and terrible had happened. That's the strange truth of gamma-ray bursts. We rarely see them head-on. What we see is the trail, the whisper, the glow after impact. And that's enough. We're still drifting. No engines, no sound, just the soft inertia of our presence here, gliding through the veil between galaxies. The stars grow sparser, the dark thickens, but that doesn't mean it's empty. In truth, this is where some of the most interesting things live. The outliers, the wanderers, the events that happen too far from home for anyone to notice. Until now. Ahead of us, in the vast dark space between two mid-sized galaxies, there's a solitary trail of heat, barely visible. Not a burst, not now, but the cooling remains of one. A ghost fire, fading from orange to grey, from grey to black, but still warm, still soft, still telling its story, if you're willing to listen closely. We slow. Just beside it is a compact knot of matter, twisted, dense, quiet. It may be a neutron star, maybe a pulsar, maybe even the early forming shell of something new, something we don't have a name for yet. It's wrapped in a swirling belt of charged particles, like a ring of smoke around a fading coal. This is aftermath. The gamma-ray burst that caused this happened roughly 300 million years ago, far more recent than most. And it wasn't discovered until recently, when a faint X-ray afterglow flared just long enough for a passing telescope to take notice. Only then did we trace its signature backward, find the scar, the bubble, the crater in the sea of gas. Here's the interesting thing. This burst didn't come from a collapsing star, not a supernova. It came from something else. A merger. Two neutron stars, spinning, spiraling, touching, and then, in one final moment, contact. In the last fraction of a second before the collision, They were moving at a significant fraction of the speed of light. Gravity was twisted into ropes. Magnetic fields exploded outward like lashes. And the instant they fused, all that mass, all that ancient dead weight, was converted into energy. That's where the burst came from. A brief, sharp gamma-ray jet fired out along the axis of collision, clean, focused, like a blade drawn through the fabric of space. That's what we saw, what Earth saw, what telescopes saw. But what happened here in this little empty corner of the universe was far more complicated. This merger didn't just make light, it made gold. Not metaphorically, literally. In the radioactive debris thrown outward, heavy elements formed platinum, uranium, europium, thorium, all the rare metals of the periodic table, all the things we think of as valuable, were created here, under conditions no laboratory can replicate. If you were to gather the dust from this collision and hold it in your palm, if you could somehow survive doing that, it would shimmer like frost in a fire. But that gold doesn't stay here, it drifts. Over time, it will be swept into clouds. It will join the formation of stars, of planets. Some of it might end up in rings, or circuit boards, or orbiting probes, or falling meteorites. The gold in a wedding band, the platinum in a spacecraft, the heavy metal inside your blood, all of it began here. From violence, value, from collapse, creation. Let's keep going. The merger site recedes behind us. The light dims again, and as we pass into another corridor of space, we find something stranger still. A spiral galaxy ahead, tilting on its axis. From this angle, it looks like a nautilus shell made of starlight layers upon layers, curling inward, folding time into a visible pattern, and within its arms, we find a mystery. A gamma-ray burst catalogued years ago. Strong, sharp, but missing one critical piece. No supernova. Most long gamma-ray bursts are followed, within days, by the telltale signature of a supernova, the explosion of the collapsing star. A delayed flash of visible light, rich in heavy elements and slower than the initial burst. But this one? Nothing. We looked, watched, waited, and no supernova came. How is that possible? There are theories. Maybe the star collapsed directly into a black hole, too fast for any explosion. Maybe the jet blew away the outer layers before they could ignite. Maybe it was a different kind of star altogether, something exotic. A population 3 star, perhaps. One of the first stars ever formed. Huge, metal-free, ancient, and now extinct. We don't know. But what we do know is this: the absence was just as loud as a presence. Sometimes, silence is its own kind of roar. And from that absence, new models were born, new theories, new possibilities. Because that's what gamma-ray bursts do. They push us to the edge of what we think we know, and then, a little further. Let's rise above the spiral now. Look down. From this height, the galaxy glows like a clock face, each arm ticking forward, each star a bead of light on a thread of time. Somewhere deep inside, another star is collapsing. Not today, maybe not for another 10,000 years, but it's close. We can feel it. Let's leave it be. We aim higher, out of the cluster, into the true dark. And here, at the edge of the cosmic map, we find a place not defined by stars or bursts, but by what isn't there. An observational gap. A region where, despite our instruments, despite our eyes, no gamma-ray bursts have ever been seen. It's not that they're not happening. They are. Statistically, they must be. But the bursts are too faint, too far, too off-axis, or maybe the light hasn't reached us yet. This is the cosmic quiet, the place between knowns. And in this place, we reflect. Gamma-ray bursts have taught us about star death, about mergers, about the production of heavy elements, about the early universe, about gravitational waves, about the structure of time and matter. But they've also taught us patience, because most of what's out there we'll never see. The bursts we missed, the ones that happened in silence, the ones whose light has not yet reached us or never will. The universe does not promise revelation, only persistence. And if we persist, if we keep watching, keep listening, keep floating through this dark with open eyes, we'll see more. We'll understand more. Because somewhere out there, right now, another star is dying. Its jet is firing, its light is coming, and it's coming straight toward us. We continue, still moving, not towards something specific, not away from anything we fear, just onward, as if carried by the gravity of knowing that there's always more to see. Out here, space stretches wide like a canvas too large for a frame, and we, still drifting in the hush between light and memory, become the quiet observers of stories written in radiation and time. Ahead of us now is not a galaxy, not a star, not even the remnants of a burst, it's something rarer. A bubble, spherical, pale, just slightly brighter than the space around it. It doesn't shine, it glows, dimly, as if trying not to be noticed. This is the remains of a burst that happened billions of years ago. We never saw it. The beam didn't point our way, but the shockwave, the gas it displaced, that stayed. This is called a GRB remnant. It looks simple, just a sphere of warm gas a few light years across. But it's not just a cloud, it's a question mark. Because here's the thing, we only recently started identifying these. We spent years thinking they were planetary nebulae, or faint supernova remnants. Only later did we realize that some of them matched the footprint of known gamma-ray bursts. The shape, the expansion velocity, the chemical content, it all lined up. It turns out, even when a burst is missed, its echo stays. And we're floating through one now. The outer layers are thin, like tracing paper. You can see the galaxies beyond, shimmering through the haze. But if you look closely just there, the gas is enriched. There's nickel, zinc, strontium. These elements didn't come from slow fusion in a star. They came from a single furious moment, a detonation, a transformation, the final breath of a giant. And they're drifting now, slowly, invisibly, becoming part of the intergalactic medium. It's beautiful in the quietest possible way. No drama, no flash, just presence. We move through the shell and out the far side. And as we do, another thought takes shape. How far away is too far? Gamma-ray bursts are some of the most distant things we've ever observed. We've seen them from when the universe was just 600 million years old, less than 5% of its current age. Their light has traveled for more than 13 billion years, through space that is still expanding, still stretching under their feet. Let's follow one now. Not with our bodies, we couldn't possibly move fast enough, but with our minds. Imagine a photon, a single particle of light born in the heart of a collapsing star during the age of reionization, back when the first galaxies were just beginning to form. That photon leaves the burst and begins its journey, through interstellar dust, past stars that haven't yet formed, past gas clouds that will one day become solar systems. That photon travels longer than Earth has existed. It crosses the forming bones of the cosmic web. It dodges the expanding edges of space. And then, finally, it touches a lens, a satellite sensor. It trips a circuit and is recorded. A single dot added to a graph, one spike in a sea of data. But that dot contains history. Because it came from a place so far away, it allows us to see into the earliest chapters of the universe's book, the chapters where darkness still ruled, where light was a rumor and matter had barely found its shape. That's the kind of reach gamma-ray bursts give us. Not just distance depth. They are among the only tools we have for probing the young universe. Their brightness cuts through dust. Their speed reveals timing. Their spectra show us what the air was made of, long before air had ever touched a planet. Let's shift again. There's another region just ahead, not filled with stars, but with something colder. A dwarf galaxy. Faint, old, metal, poor. These galaxies are often overlooked. Too small, too dim, too quiet. But some of them are where the most surprising bursts occur. Because when a gamma-ray burst goes off in a dwarf galaxy, we can study it with almost no background light. The host doesn't overwhelm the signal. It's like watching a firework in the deepest forest. The contrast is perfect. And sometimes, the burst reveals the galaxy itself. We find a flash. We look closer. And in the afterglow, we see a small, ancient system of stars we never knew was there. A galaxy hiding in the dark. In this way, gamma-ray bursts become tools of discovery. They light up more than just space. They light up our ignorance. They show us what we've missed. And isn't that the point? We move on. Down now, along the curve of a filament, one of the great invisible strings of the cosmic web. Galaxies cling to it like dew, clustered in strands. And deep in one of those clusters, there's a galaxy that's just experienced its first known gamma-ray burst. Not its first burst, the first we've seen. Because even now, with all our instruments, we still miss most of them. But this time, we were lucky. The light reached Earth on a clear night. The satellite caught it. Telescopes followed up. And now, we're here drifting above the site like ghosts. Look below. There's a dust ring forming. That's not from the burst. That's from the star-forming region around it, lit up, shocked, catalyzed. The energy of the burst may have caused new star formation nearby. The way a forest fire, strangely enough, sometimes brings new growth. We tend to think of gamma-ray bursts as endings, but in a sense, they're gardeners. Disrupting, pruning, waking up the regions around them, making room for what comes next. And what comes next? That depends. Maybe another star. Maybe a cloud of gas collapsing into a spiral. Maybe nothing for 1 billion years. But the burst has changed everything. Even silence carries its shape. Even stillness remembers the fire. We've been floating for what feels like an eternity, not through distance, but through depth, through stories wrapped in fire, through stars that died before we were born and still had something to say. We've seen the beams clean and sharp, tearing through space like the universe clearing its throat. We've followed their trails, sifted through their ashes. We've watched stars collapse, watched silence form, watched the cosmos speak in a language of radiation and time. And all of it came from something we cannot touch. A burst, a blink, a single moment so powerful it reshaped the space around it, and the science that followed. Gamma-ray bursts aren't just explosions, they're messages, not meant for us, but seen by us. Proof that the universe is still wild, still writing poetry in fire, still capable of beauty we didn't ask for and could never replicate. They are the punctuation marks at the ends of stellar lives, the fireworks that follow fusion, the warning signs and the birth cries. They are rare. They are real. They are reminders that not everything in this universe is slow and quiet. Some things happen so fast they leave only light and questions. And we fragile, curious, orbiting one yellow star on the edge of one galaxy we get to watch. We build our telescopes, we write our code, we squint at data, we stay up late chasing afterglows that last only minutes, and somehow, across the distance, we connect with something colossal, something ancient, something brief. That's what makes it all worth it. So thank you for floating through this with me, for drifting quietly through light that has crossed time to meet us here, for listening to the hush between explosions. Out here, in the dark, there is always more to see. But for now, let's rest. Let the stars whisper. Let the light fade. And when the next burst comes, wherever you are, look up. You'll know it happened. And you'll know what it means. Sleep well. We're made of this. And we're watching.